All right, let's finish up these notes. So we have this standing wave going. Again, the black is the rope. That's what you're going to see, the string, rope, whatever it is. Again, I keep mentioning demos I have at school. I wish we were there, you could see them. There are a couple videos, I'll post them as well that show a lot of this stuff anyway. Okay, so we're going to switch over to the note sheet. Okay, so this is typically how a standing wave is drawn. It looks like there are two strings here. Okay, but keep in mind that we only see, there's only one string there. All right, it's just oscillating up and down like that. So for whatever reason, that's how it's been decided to draw a standing wave. All right, we're going to determine the number of wavelengths in this image. Okay, right here. So take a moment, pause the video, look at it, think about it, and then we'll come back and discuss it. Okay, you paused, you have your answer. Let's look at this. Okay, so to determine the number of wavelengths, we have to keep in mind that this is only one string creating this. Okay, so it's like there are two different instances in time that we're seeing right here, but we have to imagine only one of them at a time. So I'm going to get, wait, maybe there's a highlighter. Let me do a highlighter. Okay. Oh, perfect. Okay, so I'm going to just look at one of these images, not both of them, and I'm going to highlight. Okay, so we start here. That would be one full wave. Now we keep going. That's a full wave. And then that's a half. So what does that mean? We've got one. Oh, I don't want that. Okay, so we've got one wave, two waves, and a half. So number of wavelengths, 2.5 wavelengths. Okay, you guys know I prefer decimals and I'm not a fraction fan because science isn't that exact, but you can see on my note sheet I did 5 halves of a wavelength. That's 2.5. It's the same thing. There's a little reason why I did that, but anyway, we'll deal with that later. So a node is defined as a point that is, I was almost going to write it, but you have it right on your sheet there, a point that is undisturbed at all times. So if we look at this, point right here, you can see it's not moving up or down. It's just there. This point, same thing, same thing, same thing. So all these points that are undisturbed, we call them nodes. So when I look at my picture here, even the ends are considered nodes. I've got a node here, a node here, 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 and here. So what is that? 6 nodes. And then antinode, you can see the definition on the note sheet. It's a point of maximum displacement or maximum deflection. So if we look at the animation here, we can see this point right here has maximum displacement from equilibrium. So this is an antinode. This is and this location is an antinode. This location is an antinode. So I'll go back to the note sheet. I've got an antinode here, one here, and really I'm looking at this location. There's an antinode, there's an antinode, and there's an antinode. So we've got 5 antinodes. Okay, do not fall in the trap. I see this all the time that some people say, oh, there's 2 antinodes right here. No, that's the same location. It's the same point, just moving up and down. So 5 antinodes. And then number of loops. It's just a terminology I'm going to use occasionally. So it's just here's a loop, here's a loop, here's a loop, here's a loop, here's a loop. The number of loops is going to match the number of antinodes. All right. You know what? And let's call that done for today. Okay. So 4.5 minutes. So I was right with my 5-minute estimate. So you can play around with these simulations if you'd like. Like I said, I'll put them in the description of the video. Also, I'm going to have at least another, well, 1, maybe 2 videos for you to watch. Again, that flipping physics guy and his 3 students that look nothing like him. It's a really nice video, so check that out. I'll put that all in the assignment for you. All right, see you later.